Hello, everyone. In today's lecture, we are going to talk about how to estimate a population mean. Okay, in section one, we are going to talk about the case estimating a population mean for with a large sample. Okay, so this is in statistics. All right, so what we do is, all right, you have a really large population. Usually, is a large and then what you want to do is you take a sample from it and got data from the sample. And for descriptive statistics, you just do some property about the sample data, like the sample mean, sample standard deviation, the median, the mark, okay, quartiles, percentiles, and so on, right? So you talk about those just to describe the statistics. And then another branch is so-called inferential statistics is to make inferences about the population based on the sample. So it's use the sample data to make inferences about the population. So that's basically what we want to do, right? So a common objective is obtain data from the sample and then use those data to form a conclusion about the population. Now, we would like to know if we want to know the mean of a population. So, for instance, the mean salary for men, right? The mean salary for women. Okay, so and so on, right? So if we want to know the mean value of a population, we usually what we do is we draw a random sample from this population and obtain the sample mean. You take a sample and get the sample mean, and then use the sample mean to as a point estimate of the population mean. So in that sense, it is an estimate of the mean is by a single number. It refers that to a point estimate of the population characteristic because it's just a single value. Okay. Now, in many cases, the sample mean is the best point estimate of the population mean. Okay, so that's the case. Now, there is a question about such point estimation is that's not going to be the exact value of the population mean. In most cases, the sample mean might be close, but it's not the same. It's not the same, all right, as the population mean. So in other words, there is an error of estimate. So the magnitude of the difference between the point estimate and the true population value in this case is between x power minus 1 denoted by this absolute value of x power minus mu. Now this error depends on the sample size and the population standard deviation. Okay, so now when we give an estimation about the unknown parameter, it is impossible to know this error of estimation because what? Because this mean is unknown, right? So we do not know the value of the mean, right? It's unknown. So how do you know the difference? Um, however, however, we can still develop a method for assessing how good the estimate is. Okay, so one of the most common methods is called the confidence intervals, proposed by Neyman in 1937. Okay, it states the following. Now, if we can find a pair of functions, all right, say the lower bar, say the upper bar, determined by this such that this probability is going to be C, all right, where C is a predetermined confidence level and V is the true value of the parameter. Okay, so then, all right, so we can figure out a interval, right? This interval, all right, this interval will give us some confidence level at C, such that we know that true value is between this. Okay, that's going to be interesting, right? So this is the idea of a confidence interval. Now, we are going to show how to find a confidence interval and how to interpret it. Um, but before we do that, we want to introduce some notifications, okay, some notations. So usually we take a mu represents the population mean, n is the sample size, x bar is the sample mean. This S is the sample standard deviation, sigma is the population standard deviation, C is the confidence level between 0 and 1. All right, usually C equals what? 90%, 95%, or 99%, right? So, or what? 0.9, 0.95, and 0.99. Okay, so the margin of error. Okay, um, now there is a concept of called the margin of error. Now, for larger samples, we mean n is greater or equal to 30, the margin of error, or the maximum error of estimate at a confidence level 100%. Okay, denoted by E is defined as follows. If the population standard deviation sigma is known, then use this one. If it is unknown, then use this one. Now, I think we know this is the population standard deviation. This is the sample standard deviation, and n is the sample size, right? They're all known. Now, what is ZC, right? So some of us may ask, what is ZC? All right. So here, ZC is the critical value in the standard normal curve for confidence level, this one, 100C. Okay, percent. It is a number in the normal standard curve such that the area between negative ZC and ZC is equal to C. Okay, so I'm going to just do this one here. Okay, draw a curve. So based on our definition, so this is negative ZC and this is ZC. Okay, so it is the value such that inside this curve, between these two, this area is C, right? Is equal to C. Okay, so that is what we have. Okay, ZC. What is ZC? Now the question is, how can we find? How can we find the ZC, right? So now using the calculator, all right, we can find the ZC as the following. ZC equals inv norm, right? It's in the T83 or 84 inv norm, and this is going to be 1/2 plus C over 2, all right, 0, 1. Okay, so this is ZC. Using the calculator, you can find the ZC. For any value given C, we can find the critical value. Now the runoff rule for E is the same number of decimal places for the sample mean or sample standard deviation. Standard deviation. Okay, it should be the same. All right, so that's what we want to runoff rule for E for the margin of error. Okay, now let's just consider how to find the value for ZC for certain confidence levels. Now consider this example. We want to find what? Z.95, the critical value for confidence level 95%. Okay, so in this case, C equals 0.95, and I have Z of C. All right, yeah, I'm going to use a calculator, right? So it's just a given here. So it's in norm 1/2 plus 0.95 over 2, 0, 1. Okay, so you should be found this one using the calculator is 1.960. Okay, and similarly for this one, when C equals 0.90, ZC equals inv norm 1/2 plus 0.9 over 2, 0, 1. So you should find this is 1.645. And finally, for C equals 0.99, ZC equals inv norm. Okay, so 1 over 2 plus 0.99 over 2, 0, 1. So it's 2.57 Sorry, I believe that's what it is, or I believe that's what it is. Okay, so we got all these values. All right, so just using the calculator, right? Plug in the value for C, plug in the formula, and we can get this one. Okay, so uh, now I want to say that these three value is worthy memorizing these. It's worthwhile to memorize these three values. All right, so when C is 0.95, it's this. Okay, so you better remember this. Now, we're ready to uh, solve some examples for the Martin error. Okay, find the following Martin errors for larger sample estimation of the population mean. Okay, so for A, we know that we want CE equals ZC times sigma is known, so we use sigma over square root of n n equals 36. So now C is 95, so ZC equals, as we see here in the last example, is 1.96 times sigma is 1.3 and is square root of 33. And then you can you can find this value. Like I do not have a calculator right now, but you can calculate this value and round to what? Round to one decimal place. Okay, you should be able to find that answer. Similarly, for this one equals what? ZC. Now, I do not have sigma, but I have S, so I'm going to use S over square root of n equals 90%. So 1.645 times S is 3.2 over square root of 40. So again, using the calculator, round to one decimal place. Now here E equals ZC times S, all right, here S over square root of n equals 99%, 2.573. I believe it's this one, all right, you may double check it with this, times 1.5 over square root of 64. So equals something this, right, round to one decimal place. Okay, so that's how we found the margin of error. Okay, so it's basically just using the correct formula and find the value for the critical values you see, right? And then just plug in the formula, you can find that. Okay, so this is the margin of error. Then the confidence interval is going to be very easy to find, right? So a confidence interval is a range of value used to estimate a parameter and stated with a specific level of certainty or confidence. Now, the following theorem gives us the procedure on finding a confidence interval. Okay, so given a random sample with size n is greater or equal to 30, we can construct a confidence interval at level this one using the following procedure. Okay, so first we check the conditions. All right, so make sure that it is a random sample and the sample size is no less than 30. So that's the condition. Okay, check those two conditions. Two is to find the margin of error. So you just plug in the formula, right? Like we just did. Okay, so just find the margin of error, round it to the same decimal place as the sample mean or the sample standard deviation. And then calculate the confidence interval. It can also be written in this way. Okay, and the interpretation. Be careful in the interpretation. All right, we are 100% confident that the obtained confidence interval actually does contain the true value of the population mean. That is the interpretation of the confidence interval. Okay, now let's consider this example. For all setting, a bottling machine delivers a precise amount of liquid. Based on historical data, the amount dispensed always has a standard deviation of sigma is 0.07 ounces. Okay, so this should be ounces. To calibrate the machine, the setting is fixed and 42 measurements are randomly selected. The mean amount delivered is 6.2 ounces with the sample standard deviation S equals 0.04 ounces. Okay, construct a 99% confidence interval for the mean amount delivered at this setting. Okay. Hint, not all information is needed. Okay. So now let's just consider this one using these conditions. Now conditions, is this a random sample? Firstly, I believe this 42 are randomly selected. So the sample is random. It's a random sample, right? And the sample size is 42. This is greater or equal than 30. So we are good to go, right? So these are the conditions we need to check. All right. So once we got the conditions, and then we need to find the margin of error. So for the margin of error, okay, so be careful. So we have two formulas, right? So now as we see, okay, so we use this one if sigma is known. Otherwise, we use the second one. Okay, so now for this one, do we know the value of sigma? Yes, it is given here, right? Now, since sigma, the population standard deviation, 0.7 is known, right? So the margin of error E equals, all right, Z of C sigma over square root of N. So Z of C is, this is 99% confident, so it's 2.573. I believe this is this one times what? 0.07 over square root of 42. Okay, now again, oh gosh, I should have my calculator with me, but I do not. So you can calculate this value, right? You can calculate this value, and remember, round to 2 decimal places, right? Because here is 2, this is 2. Now round to 2 decimal places here. Okay, so I believe you can find this E. Now the confidence interval is either you find x bar minus E, so x bar is 6.02. Okay, 6.02 minus E. Well, I do not know the values, but you can find this. X bar plus E equals 6.02 plus E. And then the interval is, the CI confidence interval is, okay, so x bar minus E, x bar plus E equals dot, dot, dot. And you can find this, right? I'm sorry, I cannot find it. And the interpretation is we are what? 99% confident that the confidence interval, or the interval, the confidence interval obtained, the obtained interval, now whatever you have here, right? So really contains the true value of the mean amount delivered at this setting, Okay, so that's what we are trying to do, right? We are 99% confident. All right, this is very important. All right, we're 99% confident that the obtained interval contains the true value of the mean amount delivered at this setting. Okay, so let's review what we did. We checked the condition, and the sample is random, n is greater or equal than 30, right? We also calculate the margin of error. Okay, since sigma is known, we use this formula, right? So remember, round this margin of error to the same decimal place as the mean, sample mean and sample standard deviation, or the population standard deviation. In this case, it's 2, right? 2 standard deviation. And the confidence interval, right? X bar minus E, X bar plus E, and interpretation. We're 99% confident that this is good, right? So that's how we solve this question, okay? Now let's consider another example. Okay, listed below are the summary statistical weights of randomly selected girls at birth based on the data from a local hospital. Okay, use this information to construct a 95% confidence interval for the mean birth weight of girls delivered at this hospital. Okay, here again, right? So is the sample is random? Yes, it is randomly selected. It's random, and n equals 36. Of course, is greater or equal than 30. So for this one, sigma is unknown. So we know that z equals zc what s over square root of n. So it is it's 95%, so it's 1.96 times s is 2.9, n is the square root of 36. And you can calculate this value. Sorry, I do not have a calculator right now, but you want to round it to, okay, I'm going to change it to 30.0. 30.0, so that it's the same decimal place. You want to round to one decimal place here, okay? And then confidence interval is going to be x bar minus e, x bar plus e. All right, you found these values. And then it's going to be x bar minus e, x bar plus e. All right, so sorry, I do not have a calculator right now, so you can find this one. Okay, so, and the interpretation is going to be, we are 95% confident that the interval, okay, so that's the same, right? So contains the true value of, so what? The mean birth weight. Okay, so that's what we have. Okay, all right, I think that's all about it. Okay, I'm gonna stop here for this lecture, and I will see you in the next one. Thank you.